Right, so we've got the object here which is going to slide down the plane. So if it slides down, of course, you've got friction acting up here. Okay, so you can see I've resolved the weight then perpendicular and parallel to the plane. So it says then when mu is 0.3, okay, calculate the magnitude of the frictional force and the acceleration of the object. So in order to achieve those objectives there, we need to resolve, of course, like parallel to the plane and perpendicular to the plane. When we resolve parallel to the plane, of course, there is movement, right? So using Newton's second law, we'll have the resultant force. So of course you've got that force going in the direction of motion, direction of acceleration. Take away then the friction, and that will equal then to mass times acceleration. Okay, so that would be like my first equation there. Perpendicular to the plane, at right angles to the plane, of course you've got the reaction here, and that will equal, won't it, the 60g cos 25. There's no acceleration perpendicular to the plane, so R will equal 60g cos 25, and that will be my second sort of equation, which is going to help me now. So because the object is moving as well, okay, friction is acting and friction is at its max. Okay, so since it's moving, I can say F equals to mu R. Okay, and then that will help me to answer then part 1 of this question, the magnitude of frictional force. Okay, so part 1 here, so we can say then the friction will equal mu. Now remember, mu is 0.3, and then you've got to times it by the reaction, which is 60g, so 60 times 9.8 times cos 25 from the second result I found there. So on my calculator, working that out, I get 159.87 newtons. Okay, that's the frictional force, and we can use that then to get the acceleration for part 2. So if we sub it in to equation 1 there, I'll have 60 times 9.8 times sine 25, take away then the friction, and that will equal to 60 times the acceleration. So working all that out on my calculator, and then of course divide by 60, and I get the acceleration out to be 1.48 meters per second squared. Okay, so in part B then it says, given that when the object is released it remains stationary, calculate the least possible value of mu. So in part A it's started to move, but if it was stationary, okay, what could we say about mu? Well, if it was stationary, of course, equation 1 here, you'd have the acceleration to be 0, wouldn't you, because it's not moving. So straight away then we could work out what friction would be. So my answer B up here, so you could say, look, from 1, since A is 0, yeah, because it's stationary, acceleration 0, you'd have 60g sine 25, take away friction is 0. So then our friction value would actually equal to 60 times g times 9.8 times sine 25. So that would equal 60 times 9.8 times sine 25. That will come out to be 248.50 if I run to 2 decimal places. Now because it's not moving, okay, friction obviously isn't necessarily at its most, okay, when it's not moving, okay. So when we think about that, we could say, look, friction is, it could be equal to its max, but likelihood is it might be less than it, so we could say less than or equal to mu r. Alright? Now, if we put that in here, and of course the reaction is the same as what we had here. Okay, so then we've got 248.50 less than or equal to mu times this, times the reaction. That comes out to be 532.91. If we take it over and divide, so we'd have 248.50 divide by this. We get out that to be 0.47 to 2 decimal places. So mu is greater or equal to 0.47. So the least mu is equal to 0.47. Okay, that's the least it can be.